Yeah, hands on everyone. Let's start off. Yeah, hands on everyone. Great. So today we'll be starting off with a new chapter, electrostatics. Again, now if you see, right, this entire electromagnetism chunk. So electro, gravity, Gauss laws. Then we have something called capacitors, current, magnetism, EMI, AC. Right. So all this stuff, this will go on, I think, almost for 3.5 months, 4 months, you can say. But this thing has a weightage of 33%. So almost one third of the questions are going to come from here, from physics. Right? I mean, at advanced perspective, you have really good questions on this, right? All the mechanics that we did so far, it's a important thing, without mechanics, you can't solve anything, but pure mechanics is around 25-30%. So that is one. And now this chapter, which we're doing electrostatics, right? Electrostatics and gravitation, both of them look quite similar, almost 80% matches. So first we will do electrostatics. That's more complex than gravitation. Then we'll go for gravitation, right? That won't take much time because the derivations look identical, so we'll not repeat them. So that saves us some time, right? And yeah, we'll go ahead with that. So we will go on till magnetism, and then maybe we'll take a small detour, and we will finish off waves and wave optics, and then we'll come back again. So anyway, so we are on par. So let's start off with electrostatics. So one thing that you'll notice, right, the difference between mechanics and electromagnetism. In mechanics, when I say the ball is rolling, the ball is moving, you actually can feel it, right? You can visualize. But here, when I say there is a charge, there is a field, it becomes a little vague. So that is one thing people generally say. But yeah, as long as you remember your standard formula, standard results, you can actually handle most of it. But anyway, let's go ahead with this. So what's electrostatics? So in electrostatics, it deals with interaction between charges at rest or slow moving charges. So basically, when charges move, right, they also generate something called magnetic field. So we are not going to deal with all that stuff in this chapter. So we are talking speed must be much, much smaller than speed of light. Yeah, generally we don't deal with such speeds anyway. So in this process, we neglect all magnetic effects and relativistic effects. So when you actually start going very fast, your mass gets messed up. Things will do change. So we are not going to deal with all that stuff there. Right? So that is one. Then, what is this? So charges are of two types. So what is charge? It's like asking what is mass. We don't know. Charges are the quantities which are responsible for the interaction between electrostatic forces. So people have seen. So these particles are interacting not because of gravity. So something new. So they started calling, okay, let's start calling them something. We started calling them charges. And we found that there are two types of them. Like I said, right, physics is always about observing something and then we just make things out of it. So if you ask what is mass, no one actually knows. We will simply say mass are the things like inertia, interaction between gravitation and all that stuff. So positive charge, the protons are one of the particles. For negative charge, we have electrons. Right? These are the fundamental stuff there. So the charge ka value is plus 1.6 10 power minus 19. I'm sure you have done this in chemistry. The charge for an electron is minus 1.6 into 10 power minus 19 coulombs. So here the units are coulombs. And the symbol is C. Now, what does the sign indicate? So be careful here. Sign simply indicates, right, they're of two different types. So when you say a plus 5 coulomb and a minus 5 coulomb, it simply means they're two different types. It's like we say, right? So you're like humans. There is a male and there is a female. So that's it. We are still humans only, but there are two categories there. Something of that sort. So sign simply indicates they're of different nature. Now, why electron is negative, why proton is positive? They just randomly said, okay, let this be positive, let this be negative, which we still regret. Because if you guys remember the definition of a current, how do we define current? The flow of positive charge is called current. But later on, we realized positive charge never flows. What actually flows are the electrons. So now what happened with the definition? The electrons are going in this direction. We will say current is going in this direction. So instead of that, if you actually said electron was positive charge, your life would have been a little better. But yeah, but since we already printed the books, we don't want to change. So you don't say plus 5 coulombs is greater than minus 5 coulombs. So this is, there is no sense for this. You can't compare. It's like I said, plus minus, these things don't mean anything. Getting it? The plus and minus simply indicate they're of different types. That's it. It's like saying which is bigger, plus 5 meters or minus 5 meters. The plus and minus simply indicate you're going front and you're going back. So there is no comparison there. All clear with this? So fundamentally, if someone asks you what is charge, we actually don't know. We just know this much. When we started doing all kind of experiments, we observed, right, these two particles, right, for some reason, they're not interacting because of gravity. So we know this is a new kind of force. We had to call something. We called it charge, and we started calling electrostatic forces. So yeah, so naming goes like that. So let's talk about more about these charges. Properties of charge. The first thing, in an isolated system, charge is conserved. Again, remember, charge is a scalar quantity. So if you have a body here, let's say we have 5 electrons and we have 10 protons. Let's say something happens and some of them combine and we get 3 neutrons, right? And we have 2 electrons and we have 7 protons. Did the charge change? What was the total charge initially? We have 10 protons, so that is 10e, and we have 5 electrons minus 5e. The total charge was plus 5e. Now, what was the total charge? It is still plus 5e. That will be 7e minus 2e. The total charge cannot change. But number of charged particles can change. So if someone asks you this question, is the number of charged particles conserved? Not necessary. But the total charge has to remain same. No matter what you do, the charge can combine, they can split, do whatever you want. It works. Second thing, charge is quantized. We got a bit of a theory. So listen carefully. The fundamentals. Now you must have heard this word a lot, quantization. What do you mean by quantization? You heard this thing in atomic structure, angular momentum is quantized. You heard this thing, the energy of a photon is quantized. So what do you mean by quantization? So the word quantization simply tells you, right? So whatever quantity that you have, it is an integral multiple of something. Meaning, think of like this. Currently in the society, right? What is the smallest denomination of money that you have? 1 rupee coins, right? I don't think people are using 50 paisa coins anywhere, right? I have not seen them from a long time, but I think if someone still gives you 50 paisa coin, we still accept it. So let's say the smallest denomination is 50 paisa coin, right? Now, what is the meaning of that is, if I said I gave you some money, you can be sure it is an integral multiple of 50 paisa coins. Meaning I can give you 23 rupees 50 paise. I cannot give you 81 rupees 22 paise, isn't it? I cannot give you 19 rupees 71 paise. So physically, I cannot give you that money. So the thing is, all the money transfers that are happening between you and me are quantized, meaning any money that I give you, it must be an integral multiple of 50 paisa coins. Is it making sense? It's like this thing. You know, when you go to a theater, right, the number of seats are quantized. You cannot have one and a half ticket, right? You cannot have two and one fourth of a ticket. You can't say, I'll just put my head inside, my body will be outside the theater, but I'm going to watch the movie. You can't get a ticket for that, right? Whether you go with a kid or something, one ticket is ticket only. So yeah, kind of like that. You got the point. So charge is quantized. That means any charge transfer. So remember that word, quantized. It's not only for this. You heard this term multiple times in multiple places. Any charge transfer is an integral multiple of electronic charge. So that means whenever you say you get a rational number like 1 by 3, no, see, that is, it doesn't work like that. Basically, see, it is like this. You actually get fraction of charges also, but those are not exactly fractions. For example, when you take HCl molecule, yeah, we write like this thing, delta plus and delta minus. It doesn't mean you actually got a partial charge. It means the charges got, little shifted to that side. It behaves like a fractional charge. Got it? In reality, the whole electron doesn't shift or something. But again, in reality, people have actually found particles which have one third of an electron charge minus two third of an electron charge. These things, they actually found these particles inside a nucleus. But yeah, in day-to-day life, you don't deal with these things. This is something when you break down, if you take protons and bombard them into each other, then you get these kind of all particles called muons, bosons, all that stuff. So anyway, we are at our level, it's fine. Let's ignore that. And anyway, think of like this scenario, like the quantity of charge is so small, right? If you say I'm giving you one third of a 10 power minus 6 coulomb charge, it really doesn't matter. It's just too small. Right? So when you say I'm giving a charge Q to a body, you can be sure this will be N into E, where N is an integer and E is 1.6 into 10 power minus 19 coulombs. Clear with this? So that is the meaning of quantization. So whenever you say this quantity is quantized, meaning that quantity you can give only as a multiples of certain limit, certain unit. You cannot give it in fractions or something like that. The third point, a very standard one, like charges repel, unlike charges attract. Fourth, free electrons are actually responsible for charge transfer. So when you say I'm giving a body positive charge, you're not giving extra protons. You cannot remove protons from inside the nucleus. What are moving is always electrons only. This is what I was saying. We should have actually named electrons as positive. We didn't realize it then. So that means when someone says this body is plus Q, it does not mean it has excess of protons. It means someone removed electrons. So if you lose electrons, you actually become positive charged. So when you say there's a minus Q charge, meaning you have excess of electrons, you gained electrons. Generally getting it, but if you talk about ions in a solution and all, that's a different story. We are just talking about solid bodies and you're giving, charges and stuff. So protons are fixed inside the nucleus. They don't come out of the nucleus. So they never participate in this kind of stuff. Yeah, protons are reserved. Next thing, charge is independent of speed. No matter how fast you go, charge doesn't change. Now, that might look weird, like, okay, what changes with speed? Mass actually changes. From relativity, if you see, the mass of a body is given by m naught root over 1 minus v square by c square. This m is your rest mass. So if you actually go really, really fast, your mass actually changes. So this is a relativistic effect. C is the speed of light. The reason you don't see this in real life is because that v square by c square, c is huge, 3 into 10 power 8. So even if you go at a speed of 1 lakh kilometers per hour, it is nothing. In the denominator, there is 3 into 10 power 8 sitting. So this is one of the problem, right? They face in this particle accelerators. So once you reach this, if you see CERN, ever heard about this thing, CERN? CERN is actually an institute, right? It is there in Geneva. So they have this the world's largest particle accelerators. So this world's largest particle accelerators, right? These things, what they do, they take two proton beams, they accelerate them to a speed of 99.93% of speed of light. And these protons, they make them go in the opposite direction and they make them bombard. And when the protons bombard to each other, right, all weird things start happening. Like they just break down into more fundamental things. And they have found hundreds of new small particles out of this. I don't know how the hell these guys do, but yeah, it's one of the world's most expensive experiment. This was established long back, somewhere in 2000s, $6.5 billion at that point of time, right? So pretty expensive stuff, right? It's a super place. Meaning, if someone is working on theoretical physics, that is your holy ground. That's your Vatican City for particle physics, something like that. That is like, yeah, the temple of that. So that is a peak thing there. Remember, I told you a story that when the sun was started, people said, there'll be a black hole formation. Do you guys remember that? I told you, and we are shouting in the class, we want holiday because Earth is going to get destroyed. You guys don't remember that? So somewhere now in that 2000s time, right? I was in school when the CERN was starting the particle accelerator for the first time. So the scientists came to the newspaper. People were asking, okay, what happens? Are there any dangers and everything? So that get told generally, like during this particle accelerator, right? When the protons collide, there is a very small probability microscopic black holes might form. And these microscopic black holes are so small, they will evaporate immediately. So nothing happens. This is what he told, complete statement. But we know na newspaper mein pura likhne maza nahi aata hai. What they did, sun activates black holes, earth will get destroyed. Right? Sun activates black holes, aliens will come from new dimension. Kuch bhi, matlab they started putting any bullshit in the newspaper. Right? And the biggest propaganda was this. They'll form black holes and the whole earth will get pulled into the black hole and will get destroyed. That was the biggest headline in almost all the newspapers next day. Some people even started putting stories like aliens will come out of the black holes and all. But yeah, I don't know. And I think I was in fifth or sixth or seventh. I don't remember. So we saw the newspaper. Next day we came to the school and we started shouting, "We want holiday! We want holiday!" The teacher came and said, "Why you want holiday?" The teacher said, "Ma'am, newspaper nahi dekha. Tomorrow Earth is going to get destroyed. So we want holiday tomorrow." We are like, teacher is like, "Pagal log, if Earth is going to get destroyed, what will do with the holiday?" I said, we all don't know that. We want a holiday tomorrow, bus. We didn't get a holiday. The earth didn't get destroyed. So, yeah. So that was the first time I actually heard about CERN that way because we thought we were going to get a holiday. Like, when you're a kid, right? What is more important, science or a holiday? The world ka, human civilization or holiday? Who cares about damn human civilization? Let them die. You just need a damn holiday. So we used to be pretty dumb kids, right? I still think about it. Then I thought, like, yeah, what teacher was saying, right? If the earth is going to get destroyed, what the hell are you going to do with the holiday? Anyways, maybe we didn't understand really what is earth getting destroyed. So anyway, those are the five properties there. So next thing. Now, so how do you get a charge on a system? So there are three ways you can create charge on a system. Again, I'm not saying you will create a new charge. There are three ways you can create a charge on one single system. So there are three ways. Charge can be created on a system. The first thing is by friction. This is a pretty common thing. You have experienced this multiple times. Maybe you must not have noticed. Ever been on a treadmill? When you catch it, suddenly you get a shock. Or ever been on this thing near an escalator or escalator? If you touch something, suddenly you get a shock. Ever felt it? So what happens, right? When you're standing, near the what do you call the treadmill, the sheet which is there, it is continuously rolling, isn't it? In this rolling ka process, right? It is rubbing this thing continuously, and when it rubs, the whole treadmill gets actually charged. So when you go and touch it, right, you suddenly get discharged. You get a small shock. If you catch it second time, you don't get a shock. Observe it, because the first time when you touch, you actually discharge the whole thing. The same thing happens with the escalator also. So anywhere where you see something, continuously moving, it is rubbing, it actually gets charged. Did you see this thing? I don't know, you must not have seen this. Next time, if you ever get a chance, observe this thing. These oil tankers which they take on the roads, oil tankers and the gas tankers. This big HP, HPCL, BP, British Petroleum, all that stuff thing, the thing. These lorries now, if you observe, they actually have a rod here. So what they do, whenever you want to take the petrol or something out of the thing, they will put the tank, they'll put the lorry there, parking may, and they will take this rod and they'll put it on the ground, and then they will open the petrol. So what happens is, because these lorries are going on a road, especially in hot summer, the road is pretty rough and dry. So when the tires are continuously moving on the road, the whole lorry gets charged, right? So there can be some charge on the lorry. Now, when you suddenly open this, and when the oil comes and hits the floor or hits the tank or whatever, there is a potential difference. You'll get a spark, and there is a chance the whole thing will catch fire. So you have to discharge it. Getting it? The biggest accident like this was Hindenburg. You should check it out. It's a 1930s ka video. I think that is a name, Hindenburg or something. It is a, this thing, the airship, the balloons, the big airship balloons. You must have seen this kind of things, isn't it? This is filled with helium or hydrogen. So during 1920s and 30s, right, these people used to travel across Atlantic Ocean in these airships. So there was one airship from Germany to US, Atlantic Ocean. It used to cross and come. So it made the full journey. It crossed the Atlantic Ocean. So before reaching, I think, New York, right, it came through a thunderstorm. So nothing happened in the thunderstorm, but the whole airship got charged. And unfortunately, right, when this thing came to the airport and when they dropped that ladder, the moment the ladder hit the ground, a spark traveled through the ladder, and this whole thing was filled with hydrogen. The whole thing got flames, and the whole thing burned down in 15 minutes. Everyone died. Hydrogen catches fire too fast, and you couldn't stop anything. You couldn't do anything at that height, so the whole thing got burned down. It's called an Hindenburg incident. You can check it out in YouTube video. It's like a 1 minute ka video. You can see it is a black and white. It's a live thing. People were recording it, so it happens. And not only this thing, moon ka surface, right, is very rough. Now the Artemis is going on, right? Artemis, right? The recent one. They're sending people onto the moon again, I guess. So the one problem they faced, the moon ka surface, there is no atmosphere. You guys might be thinking you're walking on Earth ka surface, but in reality, when you're actually walking, right, there are a lot of air molecules on the ground. You're actually stamping on them and you're walking. You're actually walking on a cushion of air molecules. On moon, there are no air molecules, so the surface is very rough. Moon ka surface is very rough. So even if you take 10 steps, you produce a lot of static charge, the whole suit gets charged up. And when this person, right, goes and touches the spaceship, he will discharge the charge, and there is a chance the sensitive equipments can get damaged. So what they do for the spacesuit, which these people are wearing, near the shoe, there is a small rod like this. So every time you walk, this rod touches the moon ka floor. So you're discharging that charge continuously. Small things. This electrostatic charge distribution is pretty dangerous. And I'm sure you must have done this in school also. Did you do this? Take a comb your hair and put near the paper. It attracts. That was actually by friction, isn't it? So yeah, if you have a cloth, right, like a velvet or something, and if you take a rod and rub it, it makes sound. Right? Cat ka skin is also good. So if you take two cats and rub them, they both get charged. So yeah, they'll scratch you and bite you, but cat also works well. So how do you get this thing? By friction, by rubbing two bodies against each other. Electrons are transferred between them. So one guy becomes positive, one guy becomes negative. So let's say if you have two identical bodies, mass m, mass m, and let's say all these are electrons. Remember, protons will never move anyway. After rubbing, one guy will become plus q, one guy will become minus q, meaning electrons have gone from here to here. So the one who lost the electrons becomes positive, the one who gains the electrons becomes negative. And because you lost electrons, your mass will be slightly small and your mass will be slightly more. Very small, but there's a small difference in mass. So if your two identical bodies are rubbed, the one with the positive charge actually has less mass. This is by friction. So whenever you rub two bodies, you can actually make them charged. Second thing, by conduction. When two conductors are connected, we cannot create fundamentally charged, right? Like remember, an isolated system charges comes out. So if you already have zero, where will you get more from? So if you bring two conductors in contact, charge will transfer till the potential becomes same. Did electrostatics start in all your classes? They still didn't start electrostatics. They should have started it by now, right? Quite an important chapter. So, for example, if you have a conductor 2q, and if you have one more conductor minus q, and if you're putting a switch, they're identical things here. Hmm. This guy will become plus q, and this guy will become, let's say this is 3q. It will become plus q and plus q. This is by conduction. So whenever you touch two conductors, charge will get transferred between them. This is what actually happens when you go and touch the treadmill. You get a shock because the charge is getting transferred from you to the thing or from that to you. All clear with these two? Friction, conduction. The third one, by induction. So when a charge is placed in front of a body, electric potential. We say a 10 volt, 20 volt, that's a potential. When a charge is placed in front of a body, it induces charge. What do you mean by that? See, for example, we have a neutral body there, and you put a plus Q charge here. So there are a lot of electrons sitting inside the body. So this plus Q, what will it do? It will attract the electrons. And in this process, what will happen? So all these electrons will start coming to the left-hand side because you're getting attracted. Think of like this. Let's say there is a big rock show or some, concert is going on, right? And if you're sitting in a stadium, what will happen? All the people will try to go to the front seats, isn't it? If everyone goes to the front seat, then you get vacancies at the back seat. Think of like this. Your teacher in the class gets some chocolates and he keeps it on the first bench. What happens? Everyone starts jumping from the back to the first bench, isn't it? Everyone wants the chocolates. So what will happen? All the electrons or all the people will accumulate in the front bench and the back benches become empty. So this becomes minus q and this becomes plus q. So you have created charges. So here electrons are attracted. But remember, it is still neutral. So if you get minus small q, you will get plus q. The total has to be still 0. And it's dipole kind of thing. And if you observe here, the plus q and minus q will attract more strongly because they're closer compared to plus q and plus q. That means you can even attract a neutral body. They attract since plus q and minus q are closer than plus q and plus small q. Now, going back to that example, air ka comb. Listen to this. When you took your comb and you combed your hair, by friction, the comb became charged. Agreed? So comb got charged because you rubbed it. When you kept it near the paper, paper was neutral, right? Why did you attract the paper? Paper didn't have charge. You're getting it? So that is actually by induction. So when you took the comb and kept near the paper, they started inducing charges on the paper, and then the paper got attracted. Making sense. So the paper didn't have any charge initially. What would happen if you put a minus q charge? If you put a minus q charge, again, same example. Let's say your classical teacher takes a stick and start beating everyone in the front benches. What happens? Everyone runs away to the back, right? So if you put a minus q charge, all the electrons here will get repelled. So this becomes negative and this becomes positive. And interestingly, you still attract because the minus and the plus are closer than the minus and minus. So you always attract. So in induction, you always attract the body generally. Clear with this? So what was the experiment that made them, figure out there is a charge? So the experiment is an electroscope. I'll just give you a brief idea about it. I'll show you also a video on this. So yeah, this is an electroscope. So here, what happens? Here you have something, these are the thin foils here. So what happens here? You have a rod. Let's say this rod has become positive charged. So when you put a positive charge near a conductor, so this here is a conductor. This will induce an opposite charge, negative. Now, because this is a negative, the whole thing has to be neutral. This guy becomes positive and this guy becomes positive. So because both are positive, they repel. You can clearly see both the metallic foils actually fly away from each other. You're getting it? So let me show you how it would look. You will understand better. So the video, right? Things are going to happen. So see that. Then I'll ask you what happened. You have to tell me like exactly what happened. Did it happen because of conduction, because of friction, or because of induction? So these are the three things that happen. So we have to figure out what. So there we have two styrofoam plates, the disposable plates, and you have a cloth. So this girl rubs the plate and puts the plate on top of another plate, and the plate flies off. The plate is simply getting repelled. Look at that again. You have two plates, you rub the plate. Now observe one thing, when you bring the plate for the first time, nothing happens actually. Then it repels. What happened? Anyone? What are the phenomena that happen? Conduction, friction, induction, what happened? So first thing, right, when she rubbed the plate, that was friction. So this is friction. So you made the styrofoam plate charged. What charge we don't know. Let's assume it became positive charge. Now when you brought the styrofoam plate close to the other styrofoam plate, now the bottom plate is neutral, the upper plate is positive. When you touch them, due to conduction, the charge got transferred between them. So the upper plate became positive, the bottom plate also became positive. Now both are like charged. And like charges will do what? They repel. So this is a phenomena of conduction and friction. This is so easy, right? You can try it at home actually. There is no induction there, it has a conduction there. Yeah, right. Okay. Look at this one. See, you're not touching the can only. This is induction. I'll put the video in the group anyway, you can see it more clearly. And there are a lot of experiments. This thing, you make a dosa on the floor with a soap solution. Then you put a bubble. And then you put the rod. The bubble gets attracted. You can move even insulated objects by induction. You can even bend water across stream also. You induce charge in the water stream, it gets attracted. This is that electroscope experiment, everyone. Look at this. You took a cork. These things will get that, aluminium foil for food wala. They kept it inside. Now initially, see, both are touching each other. Now she rubbed it, so the rod became charged. Now when you bring the charge closer to the upper one, now see what happens to the two foils there. The more closer you bring, the more they repel. You can literally see them moving. This was the first experiment. People realized, boss, this is not a gravitation. Gravitation will never repel. Right? They're always attractive. So they said this must be a new kind of force, and this must be happening due to something called charge. And that is how we started the whole story. You can even float things like this. Then look at This one and
Welcome to produce
this is how you can get good
They
hairstyle.
produce static electricity. They do a little bit something unusual to your appearance when you try them out.
So that thing on the side, right? That thing is a Van de Graaff generator. So inside there is some kind of a conveyor belt of thing. It keeps on rubbing, it gets charged. Now, why does the hair becomes like this? Think of it this way: when you touch something, your whole body becomes positive charged or negative charged. So your hair strands also become like charged, and like charges repel each other. All your hair is repelling away from each other. That's why you get spikes.
You could actually pull the top off of the Van de Graaff and look inside. What you would see is a roller at the top, one at the when we turn the
See,
belt that sits on those two rollers.
you get a new hairstyle for the girl. So the girl ka hair you can see it is all flat and this thing.
The motor on,
Now when the
that
moment she
belt
touches
starts
it,
to spin really
there
fast.
she get
And
a.
as it spins, there's a little metal cone that strips away.
Now you want to see the hair there. Nice, na? That is how hair becomes. So there, girls like even boys will get spikes also. This you can actually open in Mumbai, like you can say the Van de Graaff, electrostatic hairstyle. So we had to put some kind of a small generator in your pocket, and when you go somewhere, you switch it on, and hair becomes like this in the crowd. It might work.
So the Van de Graaff builds up a very strong.
No, we don't want explosion, we want air.
Later, they put their hand on the Van de Graaff. It steals some
You
of
have to
the
shake a bit so that things will boy ka hair
very
dekhte
person.
hain.
All of those positive charges build up in their hair, and they start to repel. Similar.
I've never felt anything like it before, and you should come out to AMZ to try it.
This is Miss
So
American Museum of Science and Energy.
now you have to think about this thing. Imagine you climb a mountain and your hair becomes like this. Means what? The whole area is becoming charged. A thunder is going to fall there. Start running from there. Getting it? So that is the first thing. You go to a mountain and you see air is becoming like spikes, meaning boss, there is something is going to fall there. You need to start running from there. Look at this thing. This is the same thing. So this guy took that plastic one and he rubbed it. Now, when you rub the whole thing, what are you doing? You're making the whole thing positive charge or negative charge. So all the strands have same charge and like charges repel. So when you throw it, see what happens. Now he's touching it, so this became the other charge. So when you throw into the air, can you see how it became? Basically, each strand is repelling each other, so you get that jellyfish kind of thing. You can actually scare kids with this when they don't listen to you. But I think the hairstyle thing was a good ray. Matlab, if you do it in, but it might work in the saloon also. Or same thing now, when when you have your hair cut and you have a hair wash, you can make them put your hand there. It becomes like this. It becomes easy to dry. So you can actually use it in multiple ways. People might even try also. Anyways, clear with this? I hope everyone got an idea about charge, right? Now this is the thing. I can't show you what is charge, but I can show you what charge can do. So when we see all these things, right, repulsion and all the stuff, that's how we know there is something called charge. So that is the issue. Unlike motion and everything, we should that. I should try that hairstyle, maybe. Great. Let's see a question. And we have 4 objects: A, B, C, and D. A is positive. That is given. A and B repel. So when you bring A and B together, they repel. B and C, they attract. B and D also attract. C and D also attract. Using this information, what is the charges on A, B, C, D? Positive, negative, so something like that. Find the charges on A, B, C, D. Yeah, simple, yeah, say a theoretical question. So there are 4 bodies, and this is what happens between them. AB repel, BC attract, BD attract, CD attract. Then what are the charges on BCD? What do you guys think? Arya got it? नहीं सम्यक हो गया बोलो ना. Wait 1 second. No, my volume is low. बोलो. You think it is not possible? Nee, Revanshika, that is wrong. Param, you got it. Trishi got it. Srihari, wrong. Aditi, wrong. I got it. Arya, got it. Utsa, tell the D part also. Maybe na, if it is actually exam, right? If you had seen the options, that would have given a big clue. Because I'm not giving options, you find it difficult, right? Obia. So what is the catch here? So when you have A, B, C, and D, one thing is clear. A is positive, that is given. B is repelling, so that also has to be positive. Now B and C are attracting, so C can be negative and D can be neutral. Remember, even a neutral body can attract. You can attract when the charges are opposite, or you can attract when one is a neutral body and one is a positive charge. But you can also have this possibility. This is positive, C is neutral, and D is negative. Now look at the options. So between C and D, one has to be negative and one has to be neutral. Then it works. That's what I said. If this is an exam, now options you'll see neutral ka symbol, na, then you would have guessed it. Because I didn't say the word neutral, you might have been thinking like, how is this possible? Clear with this? So there is that one case where a neutral body will always attract. Whether you put a positive charge or a negative charge, neutral body will always attract. All clear with this? Great. Now, the first thing that we have is Coulomb's law. So this is where we are going to get our first formula from. So Coulomb's law, what this thing says, the interaction, the force between two charges, when 2 point charges interact. So this is the valid only for point charges. The force on each charge. Is proportional to product of the charges and inversely proportional to square of the distance between them. If you have done gravitation before, right, it looks quite similar, but electrostatics is actually more powerful than gravitation, because in gravitation there is no concept of repulsion. So if you can do electrostatics well, gravitation becomes very easy. So inversely proportional to square of the distance between them. Again, this is completely experimental. So if you take two charges, Q1, Q2, let the distance between them r. This is how we write, okay? F2, 1. That means this is force on charge 2 due to 1. This will be F12, the force on charge 1 due to charge 2. And by Newton's third law, force on 1, 2 must be equal to minus of F21. Again, remember, this is valid for point charges here. So this magnitude of force is given by F is equal to 1 by 4 pi epsilon Q1, Q2 by R square. This can be also written as k q1 q2 by r square. So instead of writing that 1 by 4 pi epsilon, we'll simply call it k. So k is 1 by 4 pi epsilon. It's a constant, which is given by 9 into 10 power 9. This epsilon is called electric permittivity of vacuum. We'll talk about that more in detail. Whose value is given by 8.85 into 10 power minus 12, quite a small number there. So this is our first formula there. Means if I give you two charges, the force between them is k q1 q2 by r square. Can you see this? This kind of looks like g m1 m2 by r square. Doesn't it look like that? If you have seen in school, right, gravitation, F is equal to g m1 m2 by r square, it gives you the same vibes. So it looks the same. There, that is our first formula, everyone. We're going to play with that today. That's it. So once you know force, you can bring your entire mechanics. You can note it down. So k q1 q2 by r square. So what's the vector form for this? Yeah, that's only for vacuum. So we wrote an epsilon permittivity for vacuum. We will do it in mediums. We'll talk about that medium also. So the vector form, so this is q1, this is q2. So when you go from here to here, this is a vector going from 1 to 2. So the force on this body will be F into R12 cap. K q1 q2 by r square, and the vector will be R12 cap. That's your vector form. So if both the charges are positive or negative, you'll get a positive force. What is the meaning of a positive force? The system is a repulsion. Just understand that way. Don't worry too much about the signs. If you got a plus sign, it means they're repelling. If you got a negative force, it means they're attracting. So if you have multiple charges, let's say Q1, Q2, Q3, and so on, and if there's a small q here, so if this thing is exerting force F1, this is exerting force F2, this is exerting force F3, and this is exerting force Fn, and so on. The net force on a charge is a vector sum of all the forces. That's it. See, once you got the force, like I said, everything you learned in mechanics is valid. So this epsilon naught, this is only for vacuum. So what if it is a medium? We will see that. But for now, that's your one formula there. All clear with this? Great. So let's see a question on this. Let's get used to the formula a bit, then we will put more theory. So let's say we have a charge here. This is point A, which is 1, 2, 3. This is point B, which is 2, minus 1, 2. And let's say this is point C. And just putting random points everywhere. Minus 1, minus 2, 1. So let's say at point A we have charge plus Q, at point B we have minus 2Q, and at point C we have a charge 3Q. So there are three charges in three things there. So find force on A due to B and C. Give me the vector form, I cap, J cap, K cap. So there are three charges in the space with three coordinates. Find the force on charge A due to B and C. The net force. There, simple, straightforward vectors question. So only new thing you learned is force is K, Q1, Q2 by R square. Let's give it a try. How do we do this? See, think of like this. Forget about the value of the charges. If I just see like this, so the C is going to repel A here. So this will be one force here. This is force on A due to C, right? So I'll just call this thing FCA. So force on A due to C, right? And what is this vector here? This will be CA cap because the force is coming from C to A. What about this vector here? So what we can do, right? We can just get the magnitude and we can show the vectors in the vector form. This is a minus charge, so this guy is attracting in this direction. So this is the force between them, force AB, and the vector will be which way? AB cap. Do you guys agree with this? Minus is attracting, plus is repelling. Simple. Keep it simple. Like, let's get the magnitudes. So what is CA bar? CA bar, you know how to do this. A2 minus C, 1 minus 1, 2 I cap. 2, this thing, 4J cap. 3 minus 1, 2K cap. So we know mod CA bar, which is root over 2 square, 4 square, and 2 square. So from here you'll get CA cap, which is CA bar by mod CA bar. Great. Similarly, you want to find AB cap. So what is AB bar? 2 minus 1 I cap minus 1 minus 2 minus 3 J cap 2 minus 3 minus K cap. So mod AB bar root over 1 square, 3 square, 1 square. So what is AB cap? Take the vector AB bar and divide by mod AB bar. You're done. So what is the force AC? So FAC CA cap is nothing but K. What is the charge? Q, 3Q by distance between them, which is AC cos square. Again, remember, we are only taking the magnitudes because the vector is already taken care by this. So don't worry about the sign. So when you take force AB cap, so this will be K, Q minus 2Q. So that's what I'm saying. Don't worry about the sign. You already, when you showed it on the vector, it is already taken care of. So this is AB square. This would be AB cap. Clear this? But if you want to take the sign, then what you have to do, you have to assume even this is positive charge. Then the formula will look like this, everyone. K, Q minus 2Q by BA cos square, BA cap. So you will assume force is coming from B to A. Then you will say minus of this becomes AB cap. Understood? So it is the same thing, but you're done. So the net force on A will be, add them up. FACCA cap, FAB AB cap. I will leave it to you. You can solve that much in vectors. All clear with this? The answer will come in terms of IJK cap. Any doubts on this? Straightforward, easy vectors. So we did only one thing there. Any doubts on this? All clear? Srihari, Sudiksha, clear? Vanshika, Vedika? Great. Next one. We have a clock. And you place the charges on a clock. So at the top, we have 12Q, we have Q, we have 2Q, we have 3Q, 4Q, 5Q, 6, 7, there. So we have 11 charges like this. And exactly at the center, you kept a minus Q charge. And this radius is R. Find the net force on minus Q due to all these 12 charges. So understand one thing. Once you write k q1 q2 by r square, it becomes a vectors ka chapter. There's nothing there in electrostatics after you use that formula. So there are 12 charges, all are attracting the minus q. Find the net force on minus q. A simpler question would be this: what is the direction of the force? Options will be like towards 9, towards 10, towards 11, towards 3, towards 4, towards 5, between 3 and 4, between 4 and 5, between 9 and 8, between 9 and 10. Is all options. If you just want to find the direction. But try and give it a try. Take a minute. Let's see. No, Srihari, that is wrong. Okay, let's see. Don't guess Ray, randomly. Solve na. Why are you so busy guessing, Ray? All options are wrong. None of them are right. Don't guess. Solve. Be careful. Don't feel. This is not a feelings class. This is a physics class. Right? You want to feel. You are in a wrong class. You should go to join an arts class. There you can feel the feel. But here you have to do physics. I am having a juniors na. अभी उनके साथ वही हो रहा है. They're shouting for every damn thing. They're not even reading the question and they shout answers. They're weird. Well, I think it'll take time, 1 or 2 months. They're struggling with this also. 1/2 by 1 by root 2, they don't know what is this. They have a lot of doubts. Is this 1/2 root 2? Is this root 2? Is this 1 by root 2? I get 10 different answers for this. Karu kya matlab? I'm not understanding with them what to do. I think, yeah, can't help it. It'll take 1 or 2 months for them to do. Most of them, I think the brains got washed out after 10th board exams, I guess. Nothing is remaining in the head anymore. Told you know last time they don't equilateral triangle they don't know centroid is dividing in 2:1. They don't know ratios. If I say something is in 2:1 ratio, if I say I have to literally show them, I said this is 2/3, so 2/2 plus 1 into h is 2/3. It's like wow. They're like that. So उनका ऐसा चल रहा है juniors का and आपका seniors का अलग ही चल रहा है. Some of the idiots, I told them n number of times, don't keep random centers. So CET, some people got centers in Pune. Right. After Mumbai, Navi Mumbai, sab chhod ke Pune aa gaya center. And they're still better. Did I tell you this? I think 3 years back, there was one idiot who did this. Bits ka na, you can keep centers for options. So what options he kept? He kept one is Bits Mumbai, meaning different centers, right? He kept Mumbai, he kept Navi Mumbai, he kept Thane. These are the 3 centers. Fourth center, right? You can leave it. He said, "Chalo dekhte hain na kya hoga." He kept Dubai. उसको दुबई आ गया सेंटर. I said, "Yeah, why you want to do all this nonsense in the form filling, huh?" And the parent calls up crying, "Sir, abhi humko karna kya hai?" I said, "Sir, you have two options. One, any day, anyway, exam is in Dubai, right? You also plan a vacation there. Go write the exam and start the vacation next day. That is one good option." Second option, call the Bitska center and tell them it was a mistake. They will change it. So they changed it. But even then, I think he got some Trivandrum. They didn't have any open centers in Mumbai left. So kuch Trivandrum mila tha. I don't know whether he gave the exam or he left it. So next year when you're filling the forms, please don't do this bullshit. Oh, highlight tha. The parent calls up and says, "Sir, we got Dubai." I said, "What? Why? How the hell can you even get Dubai center?" Yeah, I said, "For a BITS exam in India." Then he told, "This idiot has built up Dubai as a fourth option." He thought fourth option kaun dega? The BITS people must have thought this guy is very interested. Let's send him to Dubai. Oh, yeah, can't do anything. Okay, anyway, let's get to this. And some of them actually got a BITS and CETICA on the same day. So there are little issues they're facing, but yeah, all are sorting out. Now, for simplicity, right, let's do something like this. Let's call F is equal to K Q small q by R square as F, right? And then it is pretty straightforward. Then you can clearly see this vector is 12F vector. This vector is F vector. This vector is 2F vector. This is 3F. This is 4F, 5, 6, 7, 8, 9, and 11. And if you observe carefully, you'll observe something. See, this is 12, this is 6. 12 minus 6, 6. 1 minus 7, 7 minus 1. 8 minus 2, 9 minus 3, 10 minus 4, 11 minus 5. Literally, the opposite vectors all will cancel out, and you end up with something like this. You end up with 6 vectors, 6F, 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 and 6F. This vector will not be there. Huh? The one near the number 6 won't exist. Now it is easy to solve, right? You got 6 vectors of same magnitude. Are you clear with this? And then how to do? And then it is done again. It's all your vectors. So we can take two vectors. So I'll take this guy and I'll take this guy, the one near the 7 and 12. What will be the angle between them? In a clock, what is the angle between two digits? 30 degrees. So the resultant of this vector will be along the bisector, and this angle will be 75 and 75. Agreed? So this resultant will be 6F 2 times 6F cos 75. And you can clearly see this is between 9 and 10. So the net force will be between 9 and 10. Let's take another two vectors. The other two vectors, one will be passing through 11 and the other guy will be through 8. This is also a bisector. Again, it will pass through 9 and 10, and this angle will be 45 and 45. So between 8 and 11, the angle is how much? 90, right? So 45, 45. So this will be again 2 times 6F cos 45. The next two vectors also, I can do the same thing. Yeah, I'm drawing a lot, but you can do this much faster. So the next one will be between 10 and between 9. Same story. So this also will be a bisector. This will be 15 and this will be 15. That will be 2 into 6F cos 15. There. So you get F net is equal to 12F cos 75 plus cos 45 plus cos 15. And the direction is between 9 and 10. All clear with this? It's all vectors, right? There's nothing big deal there. You can simplify it further if you want. You can figure it out. Any doubts on this? Clear? Take a break. Come back in 5 minutes. We'll continue from here. So there's only one formula you're playing with, k q 1 by r square. Once you got the force, it's all mechanics. Any doubts so far? Anything you want to ask? Arya.
Sir, it's not related to electrostatics, but it's like related to forces in general. जैसे कि
Hmm.
there's that you told four forces before, and you said that this one is strong and this one is weak, but I don't understand it, like why. ये 10 न्यूटन का फोर्स तो 10 न्यूटन ही होगा.
No, when this is strong and weak, it is all about interaction. Like if you take two particles, let's say mass, it's like always units. Like say 1 kg is your standard mass here, and if you take 1 coulomb as a standard charge there, the force between two 1 kgs and the force between 1 coulomb, this is huge.
अच्छा, okay, like that.
It's just a comparison.
You
It
mean to
is
keep
like
like distance same रखा तो.
हाँ सब same रख के if you just see electrostatic force and a gravitation force and you compare them.
Okay, sir.
That way they're huge. Like compared to a gravitation for a unit. Meaning, simple example, देखो ना. When you're lifting a block, let's say your phone, you're lifting it. With what forces are you lifting?
mg.
Nah, mg is not lifting it. You're lifting it. mg is pulling it down. You're
नहीं
lifting it
like
with a normal reaction and friction, isn't it?
हाँ right.
And normal reaction friction are nothing but electromagnetic forces, isn't it? They are electromagnetic forces. Now think about this. The entire earth is pulling your phone down, and just with your single hand, you're opposing earth and lifting your phone up. See?
Yeah,
You're
it's
fighting the
strong.
whole earth ka gravitation force with just your single hand ka electromagnetic repulsion. Bas, so that way when you say it is pretty strong, that's it. So bas wo comparison tha.
Okay, sir.
Okay. Chalo, come back in 5 minutes, everyone. Come back in 4 5 minutes. Go get away from the screen. I'm giving you a break for that. Go look somewhere, go out and look into the sky or see something far. Sure, let's go ahead with one more. So we have an incline here. This is angle theta. This is mu, where mu is less than tan theta. So it's less than angle of repose. Hope you guys remember what is angle of repose. And here we have a block of mass m. And this thing has a charge plus q. And here also there's a charge plus q. This is also fixed. The distance between them is x. Gravity is present. Find x if the block is in equilibrium. So normally the mg sine theta should have pulled the block down, but because both are plus, they're getting repelled. That's why the block is not coming down. So find x if the block is at rest. There, your friction and Coulomb's force. That's what I told you. Once you have force, your entire mechanics is there to play around with. Other scans on. Let's go ahead with this. Chalo, cams on everyone. So, how many answers do we have? How many answers do we have? We have done something similar. Near area. There are infinite answers. Right, somewhere. You get a range of answers. Remember this thing. Whenever you hear the word friction and equilibrium, the friction can adjust whatever value it wants. So you'll always get a range. See, let's say you bring the block very close to it. So this is plus q. You bring it pretty close to it. This is your minimum distance, x minimum. Now, if you bring the charge, block very close to it, what will happen? It will try to repel, isn't it? The repulsion force is so high, the block tries to go up. Others need to keep your cams on, or else I'll start removing you. Then the repulsion forces will be F. You have your mg sine theta. And we have your maximum friction, F max, which is mu mg cos theta. That means from here we will get K q square by x minimum square. So you cannot keep closer than this. Will be mg sine theta plus mu mg cos theta. The other extreme, let's say you keep the block very far. This is x maximum. Now the repulsion is so weak, the block will try to go down. This case, friction will be upward mg sine theta will be downward. This will be k q1 q2 kq square by x minimum square is equal to mg sine theta minus mu mg cos theta. That means you can keep this block anywhere between these two values, the x max and x minimum. You will be always at rest. You know where you guys have seen this question? In friction. ये question याद है? There is a block on an incline and there's a block on the other side. Find the value of m if the block is at rest. And then we did the same thing here. See, if they take the maximum mass, block will try to go up. If you take minimum mass, block will try to come down. You got a range of answers. So any value between 5 to 15 kgs would keep the big block at rest. Now you guys remembered? So instead of the block, I just created a repulsion force. Page 30, friction. So I'll leave it there as a reference. You can check it out. So it's the same thing. Okay, next one. Let's say we have a plus Q charge, both are fixed. You kept a minus Q charge and mass M on the bisector. This is X, this is d by 2, and this is d by 2. So if you leave the charge from there, right, find the time period for small oscillations. So basically X is much less than D. The B part, I will leave this to you as a homework. Same thing if it is plus Q and a plus Q, but this time you kept another plus Q charge, small m and mass m, and this time you displaced it in this direction. So this also will oscillate left and right. That will oscillate up and down. Find time period. Idea is the same. So let's do the perpendicular bisector. You can try the other one later on. SHM and Coulomb's force. Like I said, we just have only one formula, K Q1 Q2 by R square. Every other damn thing that you learned in mechanics will keep popping up. That's why mechanics is important. Even without weightage, it just keeps coming everywhere. Let's get this. Eight K Q by M. Nere, Arya, that is wrong. D cube आएगा. How do we get the time period, everyone? So first find the force as function of x, isn't it? Find the force between these two, find the force between these two. So get the force as function of x. You know the process in SHM. Choose your system, find the force. Then you say A is proportional to x. Try, I'll give you a minute more, then I'll show you. Show you. Let's see. C plus Q plus Q. This is your minus Q. So the force between them will be in this direction. This is F. This also will be F. Let this angle be theta. This will be theta. This distance is d by 2. This is x and this is small r. So small r is nothing but root over x square plus d square by 4. And what is F? F is nothing but k q small q by r square. Remember, just take the magnitude. The minus sign indicates the direction, which I already showed it to you, right? So yeah, that is that. Now you're great, you're done. So 2f cos theta is equal to minus mass into acceleration, because we'll always choose acceleration in the direction of x. So this is 2, f is k, q, r square is x square plus d square by 4. Cos theta is adjacent side, x by hypotenuse root over x square plus d square by 4 is equal to minus mass into acceleration. This is 2 k q q x by, that would be d square by 4 plus x square whole power 3 by 2. But since d is much greater than x, we can neglect this. Then you end up with a is equal to minus, that is d square by 4, that will become d cube by 8, that will become minus 16 k q q by m d cube into x. This looks like SHM omega square. Therefore, time period will be 2 pi root over md cube by 16 k q cube. Are the steps clear, everyone? Now let's you take k q q as theta, or q q o. Okay, and then you signed. Same thing, it works. All clear with this? What did we do exactly here? Once I wrote the force is k q by r square, electrostatics is over. After that, everything is standard stuff. Got this? Let's do B part also. Some of you didn't get how to do now. Let's do B part also. What if you take a plus Q charge and push it in along the line charge, along the line joining? Be careful, huh? If you push plus Q in this direction, what will happen? This will repel, this will repel, this charge will go away. It will never come back. You have to push it in the stable equilibrium. Let's do B part also right now. If you push that plus Q charge along the line joining them, then what is the time period? That I showed you for the vertical bisector. You guys do it for this. If you got this, I think then you understood. Try. Everyone should try.
The x is still much less than d.
Yeah, it's in a small oscillations likha tha. Remember, it will be always like that only. Like, for these all are oscillatory motions. For small x, we can say that. Let's try, everyone. Srihari, try. In case you're wondering, if you guys are a little confused, I'll just give you the starting part. You can check. So this is plus Q, this is plus Q. What you did, you pushed the charge little this side plus Q. So this distance will become d by 2 minus x. This will become d by 2 plus x. You pushed it by x this way. There. So you have to find the force on it, and then you say F is equal to ma. That is the whole story. Get it? So this will be the acceleration. So when you push it by x, the right side will repel more strongly than the left side. So you will go back to the left again. So you'll keep oscillating front and back. That's how you start. 2 pi root over 8 you got again. I think 32 you will get. I think Arya, that is right. Let's see. So what are the force on them? So let's call this guy as F2 and let's call this guy as F1. Okay. So F1 minus F2 is equal to MA. What is F1? K, capital Q, small q by D by 2 plus X whole square minus K, capital Q, small q by D by 2 minus X whole square. This is equal to MA. Take out K, QQ by D square by 4 common. You can write this thing as 1 plus 2x by D whole square 1 by 1 minus 2x by D whole square. You can actually use binomial approximation. Or you could have multiplied and ignored the x. You could have done that also. It works either way. So this is 4kqq by d square. When this thing goes up, this will become 1 minus 4x by d minus 1 plus 4x by d is equal to ma. 1 and 1 will cancel. That will be 8. It will be minus 32kqq by mdq into x. So please check. That's how you get it. Yeah. Clear? Again, did I teach you any other new formula other than k, q, and q to the r square? We'll be just playing with that. So that's what I was saying. Any doubts on this, please ask. Yeah, right, Utsa. Got it. All clear with this? Let's see one more. We have 3 pendulums. They're all suspended from the same point. Mass m plus q, mass m plus q, mass m plus q. All have same length L, L, and length L. So 3 charged pendulums suspended from the same point of suspension. And gravity is also present. Now, since all are like charged, what will happen? They will start repelling each other and they formed a shape like this. They formed a tetrahedron. What is a tetrahedron? All faces are equilateral triangle. Where did we study tetrahedron? Anyone remember? Vectors. Basic maths and vectors. This is where we studied tetrahedron, if you remember. Right? So this is the angles and all that stuff for a tetrahedron, but that's okay in case you forgot. But simple, remember, tetrahedron is simply all the faces are equilateral triangles. So how it would look. Yeah, this is how a tetrahedron looks. So basically, this is your point of suspension. So we have one string, we have second string, and we have the third string. So these strings will have tension T. Right? Find the tension in the strings. A standard mains question, you only have 2 charges. That would be an easy one. This is also fine, just a little more geometry. Is everyone clear with the picture? So you have three like charges. So if you suspend like this, they will repel, and in equilibrium, this is how they look. What is the tension in the string? Gravity is also present. Let's get this. What is theta? Actually, in this question, you can ask some really good ones. Like find the value of Q, it will form a tetrahedron. Find tension in the string. So this will not form tetrahedron for any charge. It happens for a particular charge. Right? Find tension in the string. Let me add that also. And the charge Q. So let's say Q is also not given. We need to find Q. Did you guys get the angles? So in case someone didn't get the angles, let me help you with the angles. Let's move with geometry again. So see, look at the angles. So this is point O. So from here, if you drop a perpendicular, this is going to be the centroid of this triangle, the base triangle. Okay. So if you take this and if you join this is L. This will be 2/3 of the height again. So that would be L by root 3. So if this is angle theta, so sine theta is 1 by root 3. Yeah, so if you take that as theta, but I think we can take anything as theta. I'll take this as theta better. So that would be cos theta then. Cos theta is 1 by root 3, and sine theta would be root over 1 minus cos square theta. That is root over 2 by 3. There, that's how you get the angles, everyone. So from the vertex, when you drop a perpendicular, that will fall at the centroid of the base triangle. So there, you should know your thetas there. Once you got this, then you're done basically. See the picture, how it looks. So this is the point O. This was plus Q. This was plus Q. This was plus Q. So this charge here is going to repel like this. This charge here is going to repel like this. So we have a force F, we have a force F. How much is F? K, Q, Q by L square. That's it. Once you write that, electrostatics is over. What about the tension? Tension would be this way. And what is this angle here? This angle is 30 degrees and this angle is 30 degrees. And this angle is theta. So you can clearly see the components here. If you resolve the tension into components, this would be tension ka vertical component T sine theta. This would be tension ka horizontal component T cos theta. And this is your mg. So I got T sine theta is equal to mg. And sine theta is root over 2 by 3. So that is mg root over 3 by 2. That's your tension. I got it. I took theta as that. And what about T cos theta? The T cos theta is balancing the two forces ka horizontal component 2F cos 30. Tension is mg root 3 by 2. Right? Cos theta is 1 by root 3. 2. F is k, q square by L square. Cos 30 is root 3 by 2. Yep. This thing goes off, 2 goes off. From here you get q ka value. So q square will be mg L square by 2 root 3 q. So this must be the charge to get a tetrahedron. All clear with this? I hope this picture was clear here, the FPD. So the two charges are repelling, they will be in the plane. Mg is downward, tension will be at an angle. So T sin theta will balance Mg, and the T cos theta will balance the two repulsion forces ka component. Any doubts on this, please ask me. It's more to do with visualization, isn't it? It's more of a vectors and angles and stuff. Kuch nahi, matlab, this is the only thing he used in electrostatics. K, Q square by L square. Done. Any doubts on this? Got it? So tomorrow they can ask another question, right? They'll say there are 4 charges, and they will say they form a square at the base, like a pyramid. You can keep playing around. You can keep changing the shapes. Yeah.
Sir, can you please check the calculation? I think you cancelled root 3 by root 2 for root 3 by 2.
सही बोल रहे हो. This was root over 3 by 2. I had a mistake. ठीक है. We'll get it from there. All clear with this? Any doubts on this? Clear, na? Vanshika? Trishi? Ovia? Samyak? Shaurya? Clear? Let's see one more. This was a JEE mains ka question. Standard model. Let's say we have a 4q, we have plus q, and you kept some charge q in the middle. This distance is d. This distance is x. All charges are free to move, so nothing is fixed. Then the question is, find the value of x and the value of q. So you have to keep a certain charge at a certain distance so that the whole system is in equilibrium. So you want 4q, small q, capital Q, everyone, you don't want anyone to move. System is in equilibrium. So for that to happen, what should be the value of x and what should be the value of small q? So 4q and capital Q are given. You have to find small q and x. That is the right one, Shika. Get me the charge. This was a old PYQ. Comes a lot. Does repeat. All the 3 charges are free to move. So if you're wondering exactly what's happening, right, Utsa, that distance is fine. Get me the value of Q. I'll just give you a context what is happening. See what is happening. This 4Q and this is pushing. This and this is pushing. So this has to be at rest. This 4Q and this Q both are repelling. So this small q has to attract them and put them together. So here everyone is fighting with everyone. So you need to make sure every charge is in equilibrium, meaning the 4q should not move because of q and capital Q are fighting each other. Small q should not move because 4q and capital Q are pushing each other. So you have to check it. So you have to do it for 2 charges at least. X can't be 2D ray. It can't be external. If you keep it external, what charge will you keep it? Do one thing. Give me both the answers. Give me 2D and 2D by 3 and give me the charge of small q. You will realize one thing will not make sense. Yeah, most of you are getting x. Get me the value of small q. Right, Samyak. Right, Trishi. Right, Srihari. You all got x. Right, Samyak. You got the charge also. We have one full answer. I want full answer. I want x and q together. Samyak, can you tell me, is this a stable or unstable equilibrium? The values you found, it is an equilibrium. So is it stable or unstable? Srihari, you got a minus sign wrong. Right, Utsa. This will be an unstable equilibrium. Right, Samyak? Chalo, see, let's see how to do this thing. So first thing, we will draw FBD of small q. Now, I don't know the charge of q. I'm assuming it is still positive. It could be anything. So this is 4q. This is plus q. So this guy here is pushing with a force of k, 4q, small q by x square. This guy here is pushing this way with k, q, q by d minus x whole square. And this is the easy one. Since it is in equilibrium, both should be equal. K, 4q, q by x square. K, q, q by d minus x whole square. So this will be 4 is equal to x by d minus x whole square. Put a root on that side, you will get up x is equal to 2 into d minus x. We get x is equal to 2d by 3. Okay. Then let's draw FBD of 4q. I will assume this is small q and this is plus q. So what is small q doing? Small q, I'll assume it is positive. Let's see what happens. It will push, which is k, 4q, small q by x square. Plus q will also push. Now, that can't happen. So one of them must be negative. K plus q, 4q by d square. Since 4q is also in equilibrium, k 4q small q by x square plus k 4q square by d square is equal to 0. You will end up with q is equal to, you can substitute the value minus 4q by 9. It kind of makes sense. If you think about this, the plus q in the middle must be a negative charge because 4q and capital Q will repel each other. You need someone negative who can attract them and keep them together. Have a look at this. All clear with this? Any doubts on this? It should be a minus sign, so be careful with the minus sign. Anvita, if you got 4q charge, it doesn't work. See, all three are positive charges. How can you have all three positive charges? If you have three positive charges, right? This person is repelling, this person is repelling. This will fly away. That case does not make sense. Got it? Anvita? Clear that all three positive is not possible. Any doubt so far, everyone? So this is all the forces that we got there. Now, what happens if you put forces, charges in a medium? So people have observed when you immerse this whole system in a medium, the forces actually decrease. So the formula becomes force is equal to Q1, Q2 by 4 pi epsilon medium. So it will not be epsilon naught anymore, it's epsilon medium r square. So this epsilon medium is epsilon relative into epsilon naught. So this epsilon relative is epsilon medium by epsilon naught. This is called relative permittivity, just like relative density. There is also another name for this. It's also called as dielectric constant. So what does this tell you exactly? Yeah, and this epsilon r is always greater than equal to 1. For vacuum, it is 1, and for everything else, it is 0. Just try to understand, look at the equation. Where is epsilon? It is in the denominator. Means higher the epsilon, lesser the force. So this is how you can think of. Higher the epsilon r, the more difficult for the charges to interact. It's like resistance. Somehow the medium is actually interfering with them and it is messing up the forces. Right? For vacuum, epsilon r is 1. For conducting substances, for conductors, epsilon r is infinity. We'll talk about that more detail in capacitors. So what is this F exactly? This F here is force on each charge. So let me write in the next page. So what Coulomb's law gives you is the force, net force on each charge. So this is 1 by 4 pi epsilon medium q1 q2 by r square. This can be written as 1 by epsilon r q1 q2 by 4 pi epsilon r square. And that is nothing but force in vacuum by epsilon r. That means the force between the charges on the charges will become 1 by epsilon r times, right? When compared to a medium. So when you take two charges and put them in a medium, something happens and suddenly the force drops. That would be the force in vacuum by epsilon r. Now the question comes, why is the force decreasing? Any ideas why does the force decrease? By putting in a medium, what did you do so that the force will drop? Again, you have to go back to the basics. If you take a charge and put in front of something, what does it do? It induces charge, remember? See, this is what is actually happening. When you take a charge q1, when you take a charge q2, and let's say the whole space is filled in a medium, like you take these two charges and dip them in an oil or something. This plus q1 starts inducing some positive charges here. Remember, it is a whole space here. This plus q2 will also induce more charges here. So because this center is closer, negative. It induces opposite charge. This also induces negative charge. So basically, these charges start inducing charges in the space there. And what happens? These induced charges becomes negative. They start attracting in. So you'll get F induced this way. This will be your F induced. And do remember, the two charges are still repelling each other. This force is still K Q1 Q2 by R square. They don't care about the medium. This is the same force which you had in vacuum. That means if the question was this, what happens to the force between the charges? That will never change. Think of it this way. Let's say if I'm pushing you with 100 newtons, some guy comes and pushes you with 20 newtons. Will my force change on you? Why will my force change on you? Because someone is pushing you. What will change on you? The net force. I hope you're getting the difference. If you see the Coulomb's law, right, it never gave you force between the charges. It always gave you force on the charge. Coulomb's law, if you see, the way we wrote it also, When 2 point charges interact, the force on each charge. See, I never use the word force between the charges. Force between the charges is different. Force on each charge is different. So the formula would be like this. So the force, the net force on each charge. So it is coming because of two things. It is coming because of Q2 and it is coming because of the medium. So the net force on the each charge will be the force between charges plus force due to the induced charges. So when you put the charges in a medium, they create some charges in the space and these charges started attracting them. So the overall force dropped. And this thing is F vacuum by epsilon R. This is an important concept. Right? This is F vacuum. So force between charges will always remain same. This is your F induced. So from here you can actually calculate these induced charges or the surrounding medium is nothing but F vacuum into 1 minus 1 by epsilon R. This is the force due to the surrounding medium. Again, remember, this is valid only if the whole space is covered with medium. You can't put little medium there. Because there it was all vacuum, it didn't matter luckily. When we did this 1 and 2 and everything, when it was vacuum, it worked out. Right? Yeah, but even if you take the net force, luckily they'll be equal and opposite. This is an important thing. What is the force due to the surrounding things? Clear with this? So I'll just put the statement there. So force between charges is independent of medium. So initially in vacuum, if the force between them is 100 newtons, whether you put the medium or don't put the medium, the force will always remain 100 newtons if you keep the distance same. This is independent of medium. Whereas force on each charge will depend on the medium. Just let me ask me one theoretical thing. People are exhausted already. Listen to this question. Let's say we have a charge Q1 and charge Q2. They are in vacuum. Let's say the force between them is F. Now, if you take these charges and dip them in a medium, focus everyone, don't sleep. Of epsilon R is equal to 5, right? So then what is the force between the charges? What is the force on each charge? What is the force on a charge due to the surrounding medium? What are the answers for this? What do you guys think? Sum of the force is stored on the surrounding medium. What is the force between charges? it will be still F, isn't it? Whether you put them in a medium or no medium, it doesn't matter. What is the force on each charge? It will become F by 5 because the electric constant is 5. What is the force to the surrounding medium? F minus F by 5. Are you clear with this? There, just be careful with that because I have seen, people just remember that blindly. If you put it in a medium, force becomes 1 by 5. But they don't know why it is becoming 5. They don't understand the meaning of force between charges, force on each charge, force on the charge due to the surrounding medium. So you can ask it in different ways. So that's one thing you have to be careful with. Clear? There, that would be the last one for that day. So next class, when we catch up, we'll continue from here. We'll do 1 or 2 problems on this. Then we'll go to something called field theory, which is an important one. So we will see even more good varieties in the next class. Okay, with that, we'll wrap up for the day. I'll see you guys again on Thursday. So any doubts, anything else, please stay back and ask, or else you're free to leave. So yeah, and there is an exam online, so make sure to give it before Friday.